Assalamu alaikum. My name is Hafiz Waleed Zahid, roll number 21 TE83 from Telecommunication Engineering Department, UAD TAXILA. Today we perform lab task number 4 of digital signal processing. Lab name is analyzing discrete time invariant and linear time invariant. In task A, how would you differentiate between a signal and a system? Explain the key characteristics of each and provide examples to illustrate their roles in the context of signal processing. In the context of signal processing, a signal is a system and a system are two fundamental concepts that work together to analyze, manipulate, and transmit information. Here's a breakdown of each concept along with key characteristics and example. Signal. A signal is a function that conveys information about a phenomenon. It represents a quantity that varies with time, space, or some other independent variable. Key characteristics. Amplitude, the magnitude or strength of the signal. Frequency, the rate of change or oscillation of the signal over time. Phase, the relative position of the signal with respect to a reference point. Examples: audio signal, sound waves representing speech, music, or any other audio source. Image signals, pixels values is an image representing visual information. Sensor signals, voltage variations from sensor measuring physical quantities like temperature, pressure, or light intensity. System. A system is a physical or mathematical entity that processes or manipulates signals. It can be represented by an equation or a set of rules that describe its behavior. Key characteristics. Linearity, the property where the output of the system is directly proportional to its input. Time invariance, the property where the system's behavior remains constant over time. Causality, the property where the output of the system depends only on the present and past inputs, not future inputs. Examples: filters, systems designed to selectively pass or block certain frequencies of signals. Examples include low pass filter, high pass filter, and band pass filter. Amplifiers, systems that increase the amplitude of a signal. Modulators, demodulators, systems that encode information onto a carrier signal for transmission and decode it at the receiver end. Role in signal processing. In signal processing, signals are inputted into systems to achieve desired outcomes such as filtering noise, amplify weak signals, or encoding information for transmission. Systems can modify signal in various ways, altering their characteristics or extracting specific features for analysis. For example, in audio processing, a low-pass filter system can be applied to remove high-frequency noise from an audio signal, improving its quality. In task B, how do linear time invariant system plays a critical role in digital signal processing, considering their mathematical simplicity, adherence to the superposition principle, and efficiency in the frequency response analysis? Answer: linear time invariant system play a critical role in digital signal processing for several reasons, making them fundamental building blocks in the analysis and processing of signals. Here are some key aspects of LTI system and their significance in DSP. Mathematical simplicity. LTI systems are characterized by mathematical simplicity, which makes them analytically tractable. Their behavior can be completely described by linear constant coefficient differential or difference equation. The linearity property implies that the response to a sum of individual inputs is equal to the sum of responses to each individual input. This linearity greatly simplifies the mathematical representation and analysis of system behavior. Adherence to the superposition principle. The superposition principle states that if a system is linear, its response to a sum of input is the same as the sum of its responses to each individual input. This property allows for the decomposition of complex signal into similar components, making the analysis and design of system more manageable. Engineers can understand the system's response to each component individually and then combine the results to obtain the overall response. Efficiency in frequency response analysis. LTI systems have a straightforward and coefficient method for analyzing their frequency response. The frequency response characterizes how the system responds to different frequencies in the input signal. The frequency response of an LTI system can be easily determined using a Fourier transform. This is particularly useful in DSP for tasks like filtering, where understanding how a system behaves across different frequencies is essential. Efficient frequency response analysis allows engineers to design filters, modulators, and other signal processing systems with specific frequency characteristics to meet the requirements of a particular application. Convolution property. The convolution operation plays a central role in the analysis and implementation of LTI systems. The convolution property simplifies the analysis of the output of a system in response to an input by expressing it as the convolution of the input signal and the system impulse response. In the discrete domain, Convolution can be efficiently implemented using fast algorithms such as fast Fourier transform, which contributes to the efficiency of DSP algorithms. In task C, what are the common methods for signal decomposition, specifically focusing on techniques like impulse decomposition, step function analysis, even odd decomposition, and Fourier analysis? Explore how these methods contribute to breaking down signals and their application in signal processing. Answer. Signal decomposition is a crucial aspect of signal processing, and various methods are employed to break down signals into their constituent components. Impulse decomposition. Description. Impulse decomposition involves breakdown a signal into its individual impulses. An impulse function is used as the basis for decomposition. Application. This method is often used in system analysis, especially in the field of control systems. By decomposing signal into impulses, engineers can analyze the system response to individual impulses and understand its behavior. Step function analysis. Description. Step function analysis breaks down a signal into step functions, which are functions that abruptly change value at specific points in time. Application. In control system and circuit analysis, step functions are common inputs to or disturbances, decomposing signal into step function, allowing engineers to understand how a system responds to step changes, helping in system design and analysis. Even odd decomposition. Description. Even odd decomposition involves separating a signal into its even and odd components. Even components are symmetric with respect to its vertical axis, while odd components are antisymmetric. Application. This decomposition is useful in various applications, including image processing and speech signal analysis. It simplifies the analysis of signal by separating them into components with distinct symmetry properties. Fourier analysis. Description. Fourier analysis involves decomposing a signal into its frequency components using the Fourier transform. The signal is represented as a sum of sinusoidal functions with different frequencies and amplitudes. Application. Widely used in many areas of signal processing, Fourier analysis is fundamental for tasks such as filtering, compression, and modulation. It allows for a detailed understanding of the frequency content of a signal, aiding in applications like audio processing, image analysis, and communication systems. In task D, what is convolution and how does it play a significant role in digital signal processing systems? Explore the fundamental concept of convolution and elaborate on its importance in various DSP applications such as filtering, signal processing, and system analysis. Answer. Convolution in digital signal processing. Convolution is a mathematical operation that combines two signals to produce a third signal. In the context of digital signal processing, convolution is often used to describe the process of combining input signals and with the system's impulse response to obtain the output signal. Convolution is represented mathematically by an integral or a summation depending on whether the signals are continuous or discrete. Importance in DSP. Filtering. Convolution is fundamental to linear time invariant systems, and many DSP systems are modeled as such. In the context of filtering, the input signal is convolved with the system impulse response to obtain the output signal. This is essential for operations like low pass, high pass, and band pass filtering. System analysis. Convolution is used for system analysis and understanding how a system responds to different inputs. By convolving the input signal with the system impulse response, engineers can predict the system's output for any given input. Signal processing. Various signal processing operations such as smoothing, edge detection, and feature extraction involve convolution. Convolution provides a way to combine and process signals, making it a cornerstone in tasks like image processing and speech recognition. In task E, when do we correlate two signals and what are the key applications or scenarios where signal correlation is crucial in various fields such as communication system, radar and sonar, image processing, biomedical signal processing, control system, wireless communication and seismic signal processing? Answer. Correlation of signals. Correlation is a mathematical operation used to measure the similarity between two signals. It involves comparing the shapes and amplitudes of the signal at different points in time or space. There are two main types of correlation. Cross correlation measures the similarity between two signals as a function of the time shift between them. Autocorrelation measures the similarity of a signal with a time shifted version of itself. Key applications and scenarios. Communication systems. Synchronization. In communication system, cross correlation is used for synchronizing received signal with the transmitted ones. This ensures that the receiver is sampling the received signal at the correct instance, critical for reliable data recovery. radar and sonar, target detection and localization. Cross correlation is employed to detect and locate targets in radar and sonar systems. By comparing the transmitted and received signals, these systems can determine the range, velocity, and direction of objects. Image processing, pattern matching. Correlation is widely used in image processing for pattern recognition and matching. It helps identify specific patterns or objects in images, making it valuable in fields like computer vision and object detection. Biomedical signal processing, ECG signal analysis. In biomedical signal processing, cross correlation is used for analyzing electrocardiogram signals. It helps in identifying cardiac abnormalities by comparing heartbeats and detecting irregularities. Control systems. System identification. Control correlation is employed in control system for system identification by analyzing the correlation between input and output signals. Engineers can determine the characteristics of the system and design appropriate controllers. Wireless communication, channel estimation. Cross correlation is used in wireless communication for channel estimation. By correlating the transmitted and received signal, the system can estimate the channel characteristics and admit transmission parameters accordingly. Seismic signal processing, earthquake detection. Seismic signal processing utilizes cross correlation to detect and locate seismic events. By comparing signal from different seismic sensors, the source location and characteristic of seismic waves can be determined. So in next task, we are moving to MATLAB. In this code, the function begins by prompting the user to input two signals X and H using the input function. The convolution of the input signal is then computed using the convolution function, and the result is stored in the variable Y. The code creates a figure and three subplots using the subplot function. Each subplot represents different aspects of convolution process. The first subplot displays the input signal x of n in blue. The second subplot displays the impulse response h of n in red. The third subplot displays the convolution result. Finally, the sdTitle function is used to provide a title for the entire figure, indicating that it represents convolution visualization. In next code, step-by-step convolution. The user is prompted to enter two signals X and H, which are used for convolution. These signals are expected to be entered at arrays using square brackets. The second input signal H is flipped using flip LR. The operation is necessary for convolution. The length of this input signal and resulting convolution signals are calculated. The convolution is calculated using a nested loop. The outer loop iterates over the length of this resulting convolution signal, and the inner loop calculates the convolution sum at each step using the flip and slide method. For each step of the convolution, a separate figure is created with three subplots. The first subplot displayed the input signal X. The second subplot displayed the flip's impulse response H into -n. The third subplot displays the current state of the convolution results Y up to the current step. The current step is highlighted with a marker, and the plot are updated of each iteration. The pause1 command introduces a pause of 1 second between each step, allowing the user to visually follow the step-by-step convolution process. The code includes a subfunction plot convolution step responsible for creating the subplots and updating them at each step. So this is the output. In next task, in this code, H represents the impulse response of the system, X is the input signal, and NH is the information about the origin of the impulse response, and NX is the information about the origin of the input signal. This code calls the custom convolution function myConvolution with the input signal X, its information about the origin, NX impulse response H, and its information about origin NH. The function computes the convolution result Y and the corresponding index NY. The impulse response H into N, the input signal X into N are convolved using the custom convolution function. The result Y of N and the corresponding index NY are then displayed. In last MATLAB code, shifted input signal, X shifted is the input signal that has been shifted. In this case, the origin signal X of N has been shifted by 1 unit to the right. The underscore is used to indicate the shifted element. The convolution function in MATLAB is used to perform convolution. It takes the shifted input signal X underscore shifted and the impulse response of H as inputs and computes the convolution sum, resulting in the output signal Y underscore shifted. The display function is used to display the convolution results. It prints the message convolution result for shifted input and then displays the value of Y shifted.